Hello lovely people, let me show you how I measure my things. So if you watched the last video, in the last video I went through all of this equipment that I have, how I use it and why I use it. Now I'm gonna second part is gonna be how to actually take the measurements, and later we're gonna jump into the laptop to see what kind of measurements we're gonna take and why. So first of all, let's power everything on. So I'm gonna turn on the voltmeter just to check. 13.2. This is connected, power is on. Let's flip the switch. Amp is on. I have the audio interface connected into the laptop. Now on the audio interface, this is the volume, and the connections are going like this. So I have one output that goes into the amplifier and as a loop back. And on the first channel, I'm probing one of the speaker outputs from the amplifier. And at the same time, I have these probes connected for the voltage, because I will show you why we need this. So at the moment, I have only two channels running, 1 and 2, because apparently this amp needs all 4 RCAs for 4 channels, because some amplifiers have like a switch if you want to use only 2 RCAs for all 4 channels, but this one needs all 4. So at the moment, just for testing purposes, just 2 channels are running, not all 4, but just 2. So keep that in mind. So I have everything connected like fresh. We have, let's turn the gain down, volume down, so nothing is playing at all. Let's go to REW. If I go to preferences, I'm gonna select the Focusrite audio interface. So I'm gonna choose SEO. Sample rate, I'm gonna keep it at 96K because I want to capture the harmonics down as low as possible. Now I'll choose the Focusrite ASIO. Now inputs, outputs. What I have one output and 2 inputs. Output number 2 feeds the signal to the amplifier and to the loopback. Input 1 is coming from the amplifier, and input 2 is the loopback. So we have output 1 is output 1. Input is the main one, input 1. Now timing reference by default probably it's output 2, but we're using output 1 because we're using only 1. If you would be using a different cable, you would do 2 into 2. And loopback input is number 2. Cool. So this is fine. Now what we need to do is we need to set the levels somehow. So what I'm going to do is I'm going to put the generator, and I'm going to use a scope. So this scope built into REW, you can probe channel 1 or 2, which is this. You can probe channel 1 or 2. I will be probing this channel because I need to set that amp up to clipping and a bit higher than clipping, because I want to test how it behaves above clipping as well. So I know that this audio interface gives me about 1 volt full scale 1 volt output, and this amp needs 4 volts. So all my amplifiers are going to be tested at less than 1 volt, probably even like 0.6 volts, because I'm going to tell you why. So first, what I'm going to do, I'm going to maximize the output of this that goes into the amplifier. Now the gain on the amplifier is turned all the way to the minimum. So now I need to gain match, basically, to match 0.6 or 1 volt to make sure that it outputs as much as it can. So this in REW is the signal strength. Basically 0 dB is like full tilt. However, I will be using minus 10 dB. I will explain this later why, but I'm going to be using minus 10 dB. Now, I'm going to probe channel 1, and I'm going to enable the scope. So this is now basically probing channel. If I play the 1 kilohertz sine wave, we have something wiggling around. We don't see much because it's a very small signal. So what we need to do is we need to increase the signal until clipping. So I'm taking the screwdriver. This is my gain knob, and I'm going to be turning it. And you can see on the scope, as I'm turning it, it goes up and it goes into clip. So I'm going to turn it back a bit and increase this one so I could see a bit better. Let's do 5 volts per division. Now let's do again. So I'm turning the gain knob, and here you see clipping. So I'm gonna back down. Yeah, here you see unclipped. This is clipped. I'm gonna leave it at clipped just like that, because I'm gonna stop the signal now, because my resistors with clipping, they're gonna draw a lot of power and they're gonna get warm. So I have this is a clamp meter, DC clamp meter. Look, if I play clipped signal, I'm drawing 23 amps of current with clipped. So that's a lot of current. So now I know that with this level, minus 10 dB, I have a clipped signal. So this is going to be the highest that I'm going to go to. Now, I need to calibrate it, because what's happening is in REW, you can change between different units, and I want to know the volts, exactly how many volts I have. So I did calibrate it. I didn't clear the calibration, but I'm going to show you how to do this. So I will be playing a test tone of, let's say, minus 30 dB, which is much not as loud. I'm going to play that tone. I have a sine wave, and here on this one, the speaker wires are probing. And here I see 2.315 volts, with being minus 30 dB. If I press on calibrate level and I enter this value, which is 2.315, I'm going to press calibrate and OK. And now what's happening, if I change to volts, I can choose whatever voltage I want the output to be. Instead of playing with dBs, dBFS, I can play with voltage. So if I put 1 volt, enter, I have 1 volt. If I put 15 volts, I have 15 volts. So basically I can control the voltage as I want. Now if I will put like 30, 40 volts, that's gonna be above clipped. So I need to know what is the biggest voltage that I can have. If I go to dBFS again and I put that minus 10, because remember, minus 10 is the biggest signal that I have and it's clipped. Press enter, it is clipped. And here if I change to volts, is 23 volts. So 23 volts is a clipped signal. So 23 is the highest that I would ever want to go, probably even lower, down to 20 volts. So this is now set. Everything is good. Now what I need to do is I need to check the levels on the interface. So I will be playing a very small signal, let's say 5 volts. I'm going to play the sine tone, and here I have these levels. So I have the output that is going out. Actually, I need to change dBFS, because now it shows minus 23. And I need to match the input and reference, these two, to be in the same level. So what I do, I just need to, the only thing I need to do, I need to rotate the gain knob, and basically it kind of matches all the outputs. So see, it goes green. So if I look at this and I'm turning the gain knob, 33, we're looking at this one, the input 33. I'm turning the gain knob up, 25, 22, 23. So I'm trying to match as close as I can. 23, perfect. Now I'm taking this gain knob, the second one, and I'm going to do exactly the same. Going up, 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 up. 23 something. Yeah, 23 something. So it can be like plus minus 5 or 6 dB. It doesn't really matter, but it's fine. Now I have this. What I'm gonna do is I'm gonna double check this voltage if it still is the same. So 5 volts, play 5 volts, cool. 10 volts, 10 volts. Cool. So now we know that everything is working and everything is calibrated. Okay, so after all of this, we know that we are set up this amp just above clipping at 20 something volts, which is minus 10 dB on the full scale. We know that we can control the actual voltage and it's going to be exactly as it is and on the speaker terminals. We are matching all the levels, so the audio interface knows what it's doing. And now I'm gonna show you a typical measurement that I'm planning to do. I will jump in after this into the laptop and show all the measurement, what, how, and when, but a typical measurement, how it's being performed. So I'm gonna go to RTA. I'm gonna show you where to find it, everything. Stepped sine, THD versus level, and 1000 hertz from minus 60 dB. Actually, let's change it to 40 up to 10 and 1. Okay, so this is going out. Let me, because it's gonna go off. Okay, cool. So if I run this sweep, and again, we will go through this, don't worry, I'm just showing you as an example. Okay, the sweep is running, it's checking the floor noise, and then it's checking everything else. And what we have, everything we have running. So we do have the amperage, and we have the voltage. So with every single measurement, you see, check up, down, up, down, up, down. It does the measurements, and we see voltage is going up, down, up, down. So that's specific in different levels. So this voltage is going up. See 2.5, 2.8, 3.2. So it's increasing the voltage bit by bit, and exactly the same we have with amperage. 3 amps, 3.2 amps, 3.5 amps. It's basically this specific test I'm going to show you is testing THD versus power. So it's increasing power bit by bit, and it's going to start soon it's going to start complaining. Let me show you. Okay, so I don't know if you heard that beep, but basically when D-class clips, you can hear the noise coming from the amp. So you saw it was on the highest level 20 amps of current, and this is like the test done. So basically this is how if I go to distortion, it's going to show everything. There we go. So this is how these tests are performed. Basically everything is connected, and then we're doing the actual test. So this is the part of the calibration and everything. And the only thing for me for later, we'll need to splice this cable again to have 4 RCAs. So I could drive all 4 channels, because now only 2 are driven. And this is a little bit, just barely warm, these 2 channels that are driven. And the main thing while doing this is just I need to make sure that I'm not overdriving the inputs with this, because it happened with my home amplifier, but gain is there for a reason, so that's fine. The other thing that I need to kind of monitor is the current draw, just to make sure I'm not exceeding 100 amps. But you saw, like with the sine, it was like 20-25 amps maximum. It's not an issue. And I do have a thermal probe for this that I'm planning to connect on one of the resistors, just to make sure that the resistors are not baking in there. But from what it's feeling, it's kind of fine. It's fine. And yeah, so now let's jump into the laptop. and I'm going to show you all the measurements that I'm planning to do and explain why and how. Oh, one thing that I forgot to mention, because I will be showing the actual measurements of the interface. So when I'm testing, this is testing the amplifier. When I'm testing the interface, I need to disconnect this one, and instead of that, connect, well, it doesn't really matter, basically another loop back, because I need one. So actually this is the other way around, because it's going to be confusing for you, because I know you like all the small little details, so it's just going to be confusing. So basically output 1 into input 1, output 2 into input 2, and it's basically the interface. Then it's measuring itself, its self performance. It measures how good of an output it is, and yeah, it's basically for self measuring. So this is just two loopbacks, and yeah, it's for self measuring. Okay, so in the laptop, let's go, first of all, let's go through the actual settings in this. So I showed you all the preferences. However, RTA settings are totally different than we're used to. So when we're tuning a car, what we used to do, we always have these settings. So RTA 148 with highest resolution, because we're playing pink noise. So pink noise is for RTA because it groups the frequencies together, and spectrum is different, and we have these. So for measuring amplifiers, we will need to be using spectrum mode, not RTA. Smoothing, no smoothing, FFT length, we can vary it depending on how deep into the actual floor noise we need to dig. But I found for testing amplifiers and stuff, I think 64K is going to be plenty enough. Maybe I'm going to bump it up onto 1 to 28 or 256 if I want more resolution, but we will see. Now, averages, we need to use exponential, not forever, because exponential is similar to these, like FIFO. Basically, first in, first out, it replaces, it doesn't count all of them, but it replaces some. So I found the best results using 0.94 exponential. And window, we're going to keep rectangular, and we will be changing to Blackman-Harris for one particular measurement. And max overlap, I kept it at 93. Now, another thing is, if we go to appearance here, this tab pops up, and in here we have reference resistance for dBW. So this is the, what I would imagine is the actual load that I have on the channel. If I'm testing with 4 ohm load, I'm going to put 4 ohms. If I'm going to bump it down to 2 ohm, I'm going to put 2 ohms. And this is only for when you have like different X and Y axis. And here on on X axis, sorry, you can choose watts to display watts. So if you want this value to be displayed correctly, you have to enter the correct load value in RTA appearance here. If you don't, if this is going to be incorrect, then the watts are not going to correspond with the voltage, because you can choose dBFS, which is the signal here, dBFS. Then you can choose voltage, which corresponds to the volts. And again, if you don't do the calibration, this voltage is going to be not correct. But if you do the calibration, dBFS directly translates into volts, and you have the accurate value of volts. And if you put the resistance in there, then if you choose watts here, it's going to be the actual value of watts. So now you see, when I did this experiment, when I was just playing around, I didn't put the correct value, and now I have on watts, I have 2000 watts, 5000 watts, because that value was not set correctly. But if I choose dBFS, you can see that I was playing a signal digital signal in the generator, here dBFS, all the way from wherever it is, from -50 up to 0. So let's put actually apply settings. Yeah, so -50 up to 0. And this particular measurement is the audio interface itself, how it's THD versus level. So the THD of the audio interface depending on the level of the signal. And I told you that I will come back to that -10 dB, because when you sweep, we do a sweep, the audio interface, the THD goes down, down, down. It's the lowest at about -10 dB. And then if you bump the signal up to 0 dBFS, it goes up. Now it goes up from 0.05 up to 0.1. So it's literally nothing. However, I still chose the lowest value of -10 because if we go to generator, we will be testing the amplifiers with different signals. So one of them is a sine wave, and sine wave can be from 0 dB. It reaches like these, this is actual representation of that. It reaches the tops, the peaks, and like -50 is going to be small and it's not going to reach anything. However, when we're going to be playing with different tones, for example, multi-tone, and I'm going to tell you about this a bit later, if I choose 0 dB multitone, the digital signal is clipping, because with multitones, there's a sine wave riding on another sine wave. So if you imagine like this one, and on top of that, we have multiple sine waves going up and down, and then it clips the signal. So with multitone, I believe it's -3, -4, -5, 6, 7, 8, -9. I think it's -10 that doesn't clip. Yeah, so -9 with a multi-tone that we'll be using for the testing the amplifier. With -9 dB, it clips on digital scale. And if I use -10 signal, it doesn't clip. So -10 dB on multi-tone is the highest that I can use if I don't want to clip it. And just for consistency, I chose the same level for the sine wave as well, because I could use 0 dB on the sine wave and -10 on the multitone, but I just chose just to keep it consistent. So let's have a look at a few things. These are two measurements that I did, and they are, man, it's different scaling, is it? It's basically, yeah, so different, let's -20. Just to see it better. So this, one of the measurements is, I put low level of signal and high gain on the input. And the other one is a high level signal with low gain. So if I have a lower level, you can see that, let's choose just a random value. Let's say here at 37. And if I switch to a different, you can see that the actual THD drops. So that means that in order to have more accurate measurements with lower THD from the actual sound card, I need to keep the level as high as possible and the gain on the input, the microphone input, the input 1, as low as possible. Then I will get the lowest THD from all these measurements. And I did play with loads of different stuff. I was checking like THD versus different frequencies, multitone, like sampling rate. I was playing so much with this. So like the distortion of this audio interface. So this is distortion in percentage versus frequency. And you can see it's 0.003, something like that. Another thing is the actual vertical and horizontal scaling, how you want to display these measurements. So we can use percentage for, because mainly we were going to be checking the distortion. So it can be percentage, it can be dBFS, which is the actual scale. So we can see it's minus 100 dB, the distortion. We can do dB relative, so it's relative to the signal. So relative to the signal, because on dBFS we have minus 10 signal, and this is about minus 100. But THD is not minus 100 because the signal is lower. So we choose a relative one, which puts the fundamental at 0 dB. And then we see that this audio interface has THD of 90 dB down. And the floor noise, for example, you can choose whichever you want to see. The floor noise is about like 120 dB down, and it rises with frequency all the way up to here. And we can check like the THD, the noise, and other stuff. So now let me show you actually the, is it these ones? These ones, yeah. So what I said, that when we have a measuring system, we need to make sure that the equipment that we are measuring with performs better, much better than the equipment that we're trying to measure. So this is a THD versus level of the our audio interface, and we can choose, I don't know, dB relative. It doesn't really matter, I think. Let's keep it on percentage, because I'm not sure yet what value to use. So let's keep it at percentage, and we can see that like the THD goes down, because obviously the floor noise is the same. You can see it here, the floor noise is going down. The floor noise is the same, but the noise is high. The noise and the THD total, it kind of starts to rise. So we're looking at this THD plus noise, the red line. If I untick everything and keep only this red line, so this is THD plus noise of the audio interface, and this is of the Alpine amp that I have. And you can see, just have a look at this one. So this is 0.3%, and the Alpine is at 1%. So comparing these two only, I know that my audio interface has better performance than the amplifier. If we have a look at dBFS, yeah, so on dBFS we see the Focusrite audio interface has minus 100 dB, and Alpine, the amp, minus 89. So I know that my audio interface is at least 10, has at least 10 dB lower THD plus noise than the amplifier that I'm trying to test. Now, this probably is not going to be good to test DSPs, I would imagine, because DSPs will have much higher, lower THD compared to the amps, and they might have a lower THD than the actual interface. So I'll try to test the DSPs, but I'm not sure if line level will have, probably the interface is gonna have higher THD than the actual DSP. That's my guess. And now let's have a look at the measurements that we can do. So one measurement that is the simple one is you take the generator, you play 1000 hertz at a certain level, and we capture an RTA with it. So I have a picture, for example, like this. This is the picture, that how it looks like. So this is the audio interface self-measuring itself, and we see THD plus noise 0.0043%, and we have like the fundamental 1000 hertz and harmonics. So there's one thing that we can check, is this one. Then we can do exactly the same with multitone. So if we go to multitone, and you can choose dual, triple, and multi. So this is for intermodulation distortion. We have some standard frequencies to test, or multi-tone and frequency 20 to 20K. Here we can choose the sequence length, but the highest is 64K for some reason. And we can choose decade. So decade is basically, I don't know how to explain it, but basically what's happening is with this, you have 31 tones. So these 31 tones, I would imagine, is exactly the same as Amir from Audio Science Review is testing. And it basically represents this picture. So when you have from 20 to 20K, you have 31 tones. They play on the same level, just on a lower dB scale, and you have this like floor noise. So this is on dBFS. Let me find it. Okay, I think it's this one. So I have loads and loads of measurements. So number 10, let's check this one. Yes. So number 10, let's reduce the scale so we could actually see it. There we go. And instead of SPL, let's choose, so dBFS. Oh my God. The scaling is, I was playing with the scale because I don't know what to use. Yeah, so we can see that with dBFS, we have the signal fundamental minus 25, and then the floor noise is somewhere here. But if I choose relative dBr, I have like 0, and I can see that the floor noise of the audio interface is something like that, which is like 100 dB down. So again, this is not going to be good for testing DACs or probably not even DSPs, but I think for amplifier testing is going to be perfectly enough. So let me show you a very quick example of what I've tested. So this is, actually let me show you where I found these measurements. If we go to RTA and we choose stepped sine, so stepped sine is a measurement that the REW does automatically. And what it does, you can choose from 4 of these. So THD versus frequency, THD versus level, intermodulation versus level, and multitone versus level. THD versus level is basically very explanatory. Total harmonic distortion versus frequency, not versus level of frequency. Start frequency, we can choose 20 to 20K. Now, frequency steps is how many steps we do per octave. So if we want to go all crazy, 96 steps per octave, but the measurement is going to take 700 measurements, and it's going to take ages, like 2 hours to complete. So it depends how deep you want to dig. Now you can choose the level, at which level. So this is very useful to check, is there a difference in THD, like frequency wise, between different levels, like if you play on very low level or if you play on very high level. Let me show you a very bad example of my home amplifier that I was testing. Yeah, so this is, there we go. So this is my home amplifier, THD versus frequency at 1 volt, and you can see like everything is flat. It kind of goes up a bit, but it's fine. So it stays below 0.3 on 1 volt. If I increase the voltage to 2.8 volts, this happens. So THD drops, but it's not linear, because basically with my home amplifier with higher level, with lower level, there's more noise. So total THD is a bit higher, which is weird, but yeah, that's what it is. However, it's not linear because these harmonics start to protrude. So even this was a bit higher, but it was linear. But this is not linear anymore. And if I increase the THD to 20, the voltage 20 volts, we have this. And this basically means that the THD at different frequencies is different. So this is THD versus level, versus frequency, sorry. Now, THD versus level is basically what it is. You choose a frequency at which you want to test, So we will be just testing 1,000 hertz because Amir is testing it, and I asked Gordon as well. He suggested 1,000 hertz. It's like it's an industry standard to test everything at 1,000 hertz, and the level dBFS is from -60 all the way up to -10, because -10, if you remember, is going to be a clipped signal already in my scale. And then you just choose a step how often, so every 1 dB, every 0.1 dB, every 2 dB, it depends. And basically all of these, like the FFT length and averages, overlap, this is how deep you want to dig into the noise floor. If I would choose like the biggest possible numbers, so like these would be the most accurate that REW can do, and it probably gonna dig as deep as like -20, -30 dB low in the noise floor. However, to complete these measurements would literally take a full day just to do one sweep. It's extremely like time consuming. So in order to kind of have a normal time frame, I chose these numbers, and I might slightly increase if it's gonna be needed. We will see. Okay, so this one, I found this one because I have so many measurements and they're not named. So this is THD versus level, and basically this is Focusrite, which has literally a flat THD, just a tiny bit more here, but a flat THD versus level. Now if I choose dBFS, we can choose percentage, we can choose dB relative. Again, I'm not sure what to use yet. Let's keep percentage. Yeah, so basically with this, that means that the THD kind of goes down, as I mentioned, down to -10 dBFS, and then it kind of rises up a bit. So this is for the interface. Now this is for my Alpine amplifier that I was testing. So imagine like interface goes all the way down, and Alpine has this. I think it's better to see on dBFS. Yeah, so look, on dBFS, we can see that interface has a flat THD, and Alpine has about 10 dB higher, and then it starts to rise as the level goes up. So let's do this. Let's choose percentage. And here, as I mentioned, we're testing up to -10 dB FS. However, we can choose different numbers. So we can choose the voltage, which shows me the calibrated voltage. So we can see that like this amplifier performs best with the lowest possible THD at like 7 volts. And then 1% THD is 21 volt. So again, 21 volt, if you use Ohm's law, you can calculate the wattage. However, if you remember in RTA, this appearance, when we enter this value, the Ohm value, we can choose the scale in wattage, and it shows me the actual watts. Now it's not 100% accurate because of like 4.1, 4.2 ohms and like voltage, blah blah blah. So it's not an amp dyno, but it gives you a good indication how the amp performs. So its lowest THD is the lowest between 10 and 20 watts of power, which is like ideal. 15 watts is ideal for like car application. For mid-bass, mid-range probably needs a bit less, maybe like 3, 4, but it's like the lowest. And then THD started to rise. Mainly, we will be looking at THD plus noise, because everything else is like the components that kind of adds up to the THD plus noise. So let's unclick everything and leave THD plus noise, the noise floor, the noise, and THD. There we go. So the noise, you can see it's dominated, THD plus noise is dominated by the noise. the THD itself is very low. And from this, if we take 1%, so people say that 1% THD is kind of threshold for audibility. So that means that this amplifier is extremely quiet, like the THD 0.02% at like 10 to 20 watts of power, which is amazing. And then if we take that 1%, we draw a line here, so we can tell that it gives 114 watts up to 1% of THD. Now we can check the 10% THD, but it's kind of bull, because you're not going to be listening music at 10% THD, but at 10% it gives 170 watts. At 0.1 it gives 70 watts, something like that. So again, these numbers, and in general, just a huge like disclaimer, this is not supposed to be extremely super accurate. This is just for me, for comparing different amplifiers, because I will be comparing all my amplifiers that I have, and just to have a look at this. So for comparison, have a look at this. So this is the Alpine, and this is my home amplifier, the Yamaha that I have. Can you tell the difference? So don't look at the wattage, because wattage is different, because I was testing it into an 8 ohm load. So the wattage is a bit different. This part was about like 70 watts or something, not 10, because it depends. So let's actually leave this as dBFS. Yeah, something like that. And you can see that the quietest this amp is, let's lower it down like that. The quietest, it's at 1 watt, and then THD rises. So if I flip between these, actually let's remove these just to see better. THD plus noise, noise, and this, yeah. So we can see that 1%, something like this, and the Alpine, you can see it's much more cleaner. You can see that for Alpine it starts to gradually rise, and this Alpine is a class D, and it gradually rises into THD. However, this home amplifier Yamaha that I have, it plays nice like only here, and then as the voltage rises, like if you increase the volume, THD starts to rise as well. Granted, it's only 1%, but still, like this Alpine performs much better than my home amplifier. So let's return to the actual measurements. Step sine, THD versus level, THD versus frequency. Now into modulation distortion, you can choose 2 tones. So it just does exactly the same depending on the level. 2 tones of intermodulation, but I'm interested in multi-tone. So multi-tone is that 31 tone file, and how it depends. So this multi-tone, the 31 tone file, as Amir says, it represents how an amplifier acts with playing music, actual music, not a single tone, because all of this is just a single tone. So you can see like this Alpine, for example, it has a curve like this for a sine tone of 1000 hertz. Then if I choose 2 tones, yeah, so this is for 1 tone, this is for 2 tones, and you can see straight away that the distortion increases. And this is for the multi-tone, so sine tone and multi-tone. So you see it has, I don't really say it has problems here, but basically up to 1% THD, it can shoot out only 24 watts, but with a sine tone, it's clean up to 116 watts. And with music, it's clean up to 25 watts. This is 1% THD with multi-tone. However, take into account that this is, as I mentioned, spectrum is not RTA, because with RTA, with music, you have minus 3 dB per octave going down the signal. So you're not gonna have this much level of THD with music. This is literally sine tones, so it's a slightly different. But basically, these are the main measurements. So THD versus frequency, THD versus level, and multi-tone. I'm not sure if I'm going to test that into these with these two levels, but I will be testing with multi-tone. So this video, oh man, it's so long, but basically this is how I'm going to be testing. If I will see that the performance of the amplifier is very close to the actual audio interface performance, I'm going to increase these numbers. So because like this test, if I just let it run, for example, it's not going to do anything probably. So this with basic measurements, it's just measuring random stuff, but it doesn't really matter. It takes what, maybe about 4 to 5 minutes, like 51 measurements. It says time remaining. Does it say how much? 2.5 minutes. So this is 2.5 minutes for one test. However, if I will increase those numbers like very high, it's going to take maybe 10-20 minutes, half an hour. So if I will see that I will need more accuracy, dig deeper into the noise floor, then I will be increasing this, and the measurements are going to take half an hour if they have to. So probably one full day for a single amplifier testing. So yeah, with this, I will be measuring very different things. Oh, this is just for you to show the floor noise that I captured with just with RTA, not with a sine, step sine, but just with RTA of Focusrite and the amplifier. And the floor noise is kind of the same. I don't know. Maybe something to do with my measurement methodology. I don't know. But yeah, it is what it is. So I will be testing very different things, like how RCAs impact the signal. If we would have like that shitty bad power supply that I have, if I would have it connected to the lithium battery, does it affect the measurement? Does it influence? Then I will be testing like 2 ohms versus 4 ohms. If you have a lower impedance speaker, does that affect amplifier performance? And if it does, by how much? And like, I'm planning to do very different things. And I do have quite a few different amplifiers. I'm going to talk about them a bit later. But yeah, I think it's going to be very fun to test this. Yeah, if you have any suggestions, if you have any tips, if you have any questions, please comment below. I'm happy to answer all of them. And I guess the next video is gonna be presenting the actual measurements of one of the amplifiers, and then I'm gonna do like one by one all the amplifiers and comparing, because I need some kind of methodology, like how to compare them. Do I compare them in percent? Do you compare them in dBr? Do I display watts, volts? I don't know. I need to decide on that, just to keep everything consistent so that I could literally compare stuff. But yeah, this is pretty much it. Very good function, RTA, step sine, and basically it does similar things that a that interface that Amir has and other stuff. How is it called? I don't remember anymore. Yeah, I think it's gonna be cool. Very cool. So thank you very much for watching, and I will see you in the next one.